Right. So seems like this year you guys are all quite lucky with the fire alarm and power outages. I think universe really hates the midterm two. So the way we're going to do midterm two this year, and so I'm not going to release the solutions for midterm two tonight because I'm still waiting for online folks to finish their midterm two. Um, I want them to take it seriously because you guys also had to take it seriously until the last 10 minutes. Uh, what I'm going to do is once I release the solutions, I'm going to create a grading rubric, and I want all of you to assess your own midterm. Like honestly, catch the mistakes you made. If you made mistakes or didn't finish a problem, finish it. You can use the grade, you can use the solutions if you want, and then I want you to submit it. I'm going to create this as a submission, so you can now submit it through midterm two. You can submit your corrections. I'm going to review your grading. If you were honest with yourself and honest with your grading, you'll just get full credit, 100%. So there's no stakes. So you don't have to like lie or fluff up your midterm. It's fine. I want you to learn the concepts I covered in midterm two and also kind of like look at the strategies of solving midterm two. If you look at the solutions, it's a you should be able to do most of the problems without a calculator. You can just kind of see through my techniques of how I write my exams as well. So hopefully it'll prepare you better for the final exam. Um, so I'm gonna try this out this year and see how that goes. I think that it just got complicated with grading when with the fire alarm and the power outages. I just don't want people stressing over this too much. It's just an exam. Um, so in regards to homework eight, I'm going to postpone homework eight. So it's going to be pushed to homework eight is going to become homework nine. So we're only going to have eight homeworks this quarter, but homework eight is going to be due after the holidays. It's going to be a little bit heavier, so it's going to be probably 4 or 5 problems instead of the two right now. And then this grading is going to be due next Wednesday. So I know I said no homework due during Thanksgiving. This isn't homework. This is midterm two still. So technically, I'm still right. But I think it's a small compromise you can make. And you'll have the solution. So it's not like you'll be spending that much time to grade it because in theory, you should be able to finish this in 50 minutes, probably more like an hour and 20 minutes or hour and 30 minutes. And with the solutions, you should be able to finish it even faster. Uh, so I'll release the solutions after midnight tonight once the online exam people finish. And then the same rule will also apply to online exam people as well. So you're just going to take your exam and grade it and then submit it. And I'll have a rubric. For people who have not picked up the midterm or are online, what I will do today is I am going to scan the rest of those and then I will upload it or I'll find a way to send it to you. I might email it to your UW email. If you can come tomorrow in class and grab your exam, that would be helpful because it's still quite a bit of exams for me to scan. So if not, no worries, I'll send it to you. Any questions on that? All right, cool. So I'll make the announcement after class as well, so that way you can have it in writing. And yeah, let's get started. So we started Bode plots yesterday, or we started last Wednesday, but then we continued it yesterday. And I guess one little note I want to make about drawing poles and zeros. So it's a little extra note here. Is that so yesterday when we drew a zero, we can see that magnitude is increasing and we're increasing our phase in the positive way. And when we have a pole that's negative, we're decreasing our magnitude and we're decreasing our phase. So positive phase is a phase lead and negative phase is a phase lag. When we're adding a pole or zero that is in the left half plane. One thing I want to talk about real quick is our lead compensator and lag compensator, and this is the reason why they're called that. So when we look at a lead compensator, let's look at maybe a simple one where we have GFS is equal to S plus 2. So we have a 0. And for it to be a lead compensator, I guess I should use C of S. I'm going to call this C lead. And then we have a pole at 10, minus 10, I mean. And I guess like we haven't done any examples on when we have more than one pole or 0, but basically you just sum up the asymptotes of the angles and you sum up the magnitude, the slopes of the magnitude as well. Let's just look at the phase because we don't really care too much about the magnitude so much. We care more about the phase because this is what makes a lead compensator a lead compensator. So as a quick recap, when we have a pole in the left half plane, we go from 0 to minus 90 degrees, and we start at 10 times before the break frequency and stop the change in phase 10 times after the break frequency. It's the same with zeros, where we start at 10 times before the break frequency and we stop at 10 times after the break frequency. So since we have a 0 at 2, that means we're going to have the change in phase at 10 times 10 to the negative 1 power times 2. So we have 10 to the negative 1 power. And then the way log plots look like is like they look like this, where we have these notches getting closer, closer, and closer to each other. Then we have another decade. So you have like 10 to the 0, then we have 10 to the minus 1. There should be 10 notches, but I cannot count. 1, 2, 3, 4, 5, 6, 7, 8. I think I'm missing one. Something like that, right? That's what like a log plot looks like. So then this is 1 times 10 to the 0. This is 2 times 10 to the 0. This is 3 times 10 to the 0 until you reach, that should be 10 to the 1, until you reach all the way to the next decade. So right here, we're going to have 2 times 10 to the minus 1. And then I'm going to jump to the next decade, which is put 10 to the 0 here. It's kind of hard to draw a log scale. And then we're going to have our break frequency at 2, which is right here, roughly 2 times 10 to the 0. This is our break frequency of our 0. And then we're going to go to 10 to the 1 power now. So that's 10. Let me make this a little longer. Then I have 10 to the first power times 2. Or 2 times 10 to the first power. And then we're going to go all the way to 10 squared. So that's 100 because we're looking at our phase. For our 0, we care about 2 times 10 to the minus 1 all the way to 2 times 10 to the first power. But then for our pole at 10 or at minus 10, we care about 10 to the 0th power to 10 squared. That's going to be our range of asymptotes that will have change. And I'm going to denote the 0 by a red asymptote. So we're going to hit our break 10 times before the break frequency, and then we have a change of 45 degrees per decade. So 45 degrees is going to be around here, and then another plus 45 degrees right there, and then flattens out. So we're going to draw a line connecting this dot right there. Okay, now when I'm drawing my pole, I'll denote that by purple. We're gonna have our break frequency as at 10, so that we're gonna have the change in phase at 10 times smaller than 10, so at 1, and it's going to change by minus 45 degrees for two decades. And then it's going to flatten out. So these are how our phases change individually. And then when you think about our phase is going to be phase of C is going to be equal to the sum of the angles of the zeros minus sum of the angles of the poles. So what we're going to do here is we're going to add up these asymptotes. So the addition of the asymptotes is going to be in green. So here, there's no change in phase, and then now we're increasing the phase by 45 degrees. But then, maybe I'll make this a little bit thicker. Oh yeah, so the break frequency is going to be for the magnitude, but then the break frequency for the phase is 10 times smaller than the magnitude, and then stops at 10 times past the break frequency. So if we look at the previous example where we have the pole at A minus A, so 10 to the 0 times A is the break frequency, but then for the phase, the change occurs at 10 times smaller and ends at 10 times bigger, roughly. In reality, it's constantly changing, but these are our asymptote lines that we use as reference points because as frequency changes, our angle will change as well when we're evaluating the angle because of this equation. But it will never pass minus 90 or 90 degrees in this example. Each contribution from each pole and zero only changes by 90 degrees. Okay, so we draw this line, and then we can see that we have our zero at 45 degrees per decade, but then our pole here also subtracts 45 degrees per decade. So then we end up going flat here until we hit the end of the zero, because the zero is now no longer contributing any change in phase. So now the pole is subtracting 45 degrees until we hit around there. Yep. So then, but then once the pole also stops changing, it just flat lines like that. And this is our total phase. This is our total, or this is the phase of G. This is the phase of G or C here. So here, if you look at this system, the C has a net positive of 45 degrees, like right here. This is like the most phase lead you can get from the system is 45 degrees, and there's no phase lag in the system at all. So this is why this is called a lead compensator. So I'm going to highlight this region here. So this is all phase lead. And this is why we call this a lead compensator. And same with the phase lag. When we have the pole appear before the zero, we're going to have a change in the phase in the negative direction before the zero will put it back to zero again at higher frequencies. And that's called a phase lag or a lag compensator because we have a lag in the phase. And the way phase lead and phase lag shows up is time delays. So phase lag will have a time delay. Phase lead will reduce time delay, but you cannot have a system that reacts before the input occurs. So there is no true phase lead system. All this is doing is it's reducing the lag of the system we're trying to control. Okay, so just a little side note on that. Any questions? I have the same ringtone. I think it's for line. Anyway, so what about Bode plots for higher order systems? So, we talked about this briefly. So that last example showed how we can have different break frequencies. We just draw the asymptotes for each individual pole and zero, then we add them up. At least for the phase. For the magnitude, we add up the change in slopes instead. So the reason why we like to factorize it first is because it allows us to identify breakaway frequencies, and we can take advantage of taking the log of G. And by taking the log of G, we're just subtracting the values of the numerator, or we're taking the values of the numerator and subtracting by the denominator or adding it, depending on the properties. Uh, One other thing about this is that when we factorize it, so here we actually have a bunch of real poles and zeros. Um, but you can also factorize it as a product of a bunch of real poles and zeros and complex conjugate poles and zeros as well. Um, I guess this PI and P or PJ and ZI are not specified. So I guess the ZI and PJ can be complex as well. And so when we have it in the factorized form, we take the log of it, we can do log of all of the zeros added together minus log of the poles um, subtracted. And the phase is just going to be the phase of the zeros minus the phase of the poles. And then yesterday, so this is where we left off yesterday, where I talked about how to use this table, and I'm going to go over a special case of when you have a pole at the origin and a zero at the origin. So zeros and poles at the origin only add a constant phase to the system. Uh, yeah, if you think about like this, right? If you have so if g of s is equal to z, or no, sorry, not z, is equal to s. And when we put it in the Bode plot, we get g of j omega. So we let s is equal to j omega, and we get j omega. So this is for zero at the origin. Then when we look at the phase of this, it's going to be the arctan of the imaginary divided by zero. The imaginary component divided by zero. That goes to infinity, so that's 90 degrees. Because when we're evaluating this on the complex plane, I'll draw it down here. If we have a zero here and we're evaluating it at this point, yeah, it's 90 degrees. So now we look at the pole. G of s is equal to 1 over s. And so then we do the same thing. It's going to be 1 over j omega. And the rule about the phase of poles is that the phase of poles is equal to the zeros minus the poles minus the angle of the poles. So we just evaluate the angle of this pole like we did with the zero. It's still the same. It's going to be equal to minus tan arctan of um, omega over zero, which is just not minus 90 degrees instead. I mean, the proof is here. If I were to multiply the top and bottom um by j, then I get minus J over omega. So then the angle is just going to be arctan of minus 1 over omega over zeros, which is still minus 90 degrees. I guess this is wrong. Oh, no. You know what? We're just going to leave it. Okay, so that's why the phase is always 90 degrees regardless of the frequency, so it's invariant with the frequency. Now, for the magnitude is where it gets tricky because when we're taking the magnitude of this, so we do the zero first. Magnitude of G of J omega is going to be equal to, that's pretty easy, just omega, right? So then when we do it, our magnitude plot's going to be 20 log scale of omega. I'll draw on the right hand side. So I'm going to draw my phase underneath as well. Might get a little crowded. But try to fit everything on one page. This is going to be my logs, my magnitude plot. And my phase plot. And we're going to have, start with 10 to the minus 1, 10 to the 0, and 10 to the first power. So we want the lines to align for the phase and magnitude. 10 to the 0, or 10 to the minus 1, 10 to the 0, and 10 to the first power. So this is going to be our magnitude. And then our phase. Maybe I should write. Yeah, I'll just write decibels. So let's do the 0 first, where basically we can't set omega equal to 0 because that's undetermined, undefined. Taking log of 0 does not exist. So we need to find a point where we can evaluate. I can actually let omega equal to 10 to the minus 1, but I actually find it a lot easier if I just say, what if we just let omega equal to 0? Then what we can see here is that 20 log of 0 is equal to, or sorry, not 0, 1. 20 log of 1 is equal to 0 because log of 1 is equal to 0. So this is 0 decibel. This is also called the crossover frequency, where the frequency crosses 0 decibels. And I'm going to denote it by this blue line here. And the nice thing about this is this is my starting point. Or not, a better term would be my reference point. This is not defined in the textbook. I just call it a reference point. And the reason why I like this point is because I know that zeros in the origin rise with a magnitude of 20 decibels per decade. So now that I have my reference point, it's just going to be a 20 decibels per decade slope. Maybe I'll make this a little less steep. But this slope here is 20 decibels per decade. So maybe if I were to reference this point here, this is minus 20 decibels. So it goes from minus 20 decibels at 10 to the minus 1 to 0 decibels to positive 20 decibels at 10 to the first power. Now, it's the same with the pole. I'll use screen here instead. If I do the pole, it's going to be 1 over omega. And so then what we're going to get is 20 log of 1 over omega, which is just equal to minus 20 log of omega. Same thing. Omega is equal to 1. We get 20 minus 20 log of 1, which is equal to 0. Same starting point. But now we have a slope of minus 20 decibels per decade. So if I were to look at the phase plot here, the phase plot of a 0 is going to be 90 degrees. It's going to look like that. Phase plot of the pole at the origin is going to be minus 90 degrees, which is going to look like that. Let's say I have a third system where g of s is equal to 1 over s squared, where I have two poles at the origin. It's going to have the same reference point because when I take the phase of it, it's going to be, the magnitude is going to be 1 over omega squared. So then my magnitude is going to be minus 20 log of omega squared, which is equal to minus 40 log of omega. You can see here, this minus 40 means I have a slope of minus 40 decibels per decade as compared to the 20. So then I still have the same reference point, but now I'm going down at minus 40 decibels per decade. And because it's a log scale, all you have to do is you just add up the change in slopes for each pole that in 0 you have. So this is minus 40 decibels per decade. And the phase also just adds up. So now that we have two poles each contributing at minus 90 degrees. So you add them up, which is minus 180 degrees. Any questions? Okay. All right, so this is my table. So yesterday I talked about briefly how to read this table. Let's go over again. So if depending on your 0 or pole, you can have a positive 0 or negative 0. Positive pole or negative pole has no change in the magnitude because we're taking the square of it, but it does change the starting location of the phase. So you have a positive 0, and then you have a phase of 180 degrees as your starting point. If you have a positive pole, you have a starting phase of minus 180 degrees, and even the change in phase is going to be different. And you only have a change in phase by 90 degrees total per 0 and per pole, meaning that each 0 can only change your system's phase by 90 degrees or minus 90 degrees, each same with the poles, and that the change in phase starts at 10 times before the break frequency and ends at 10 times after the break frequency with a change of 45 decibels per decade or 45 degrees per decade, either minus or positive. So I guess maybe a few extra notes on this page that I added next year. So we're given a pole or 0. If g of s is equal to 1 over s plus a, or S plus A. So A is going to be called the break frequency. Um, so at the break frequency at omega is equal to A, magnitude changes by either plus or minus 20 decibels per decade, depending on your polar zero. Or maybe a better way of saying it yeah, at, yeah, per pole slash zero. I guess the way I wrote plus minus should be per zero slash pole. For the angle asymptotes, angle asymptote changes to plus or minus 45 degrees per decade. At omega is equal to 0.1 A. And I guess like flattens out. So where we no longer have that change, flattens at omega greater than or equal to 10A. So in other words, we no longer have a change in phase after 10 times the break frequency. Are we good with this table? Any questions on how to read it? Okay. So now that I have an example of this Bode plot, one thing that you can do, and maybe I think I might have a handout of this plot here, is when you do homework 8 eventually, if you remember this material after Thanksgiving, you can print out the Bode plots and just draw it on this, or you can, draw manually on like that if you want, if you hate yourself or something. It's like, and hate the graders. But yeah, this is going to be a lot easier on the final exam. Usually I have a printout of this if I do have a Bode plot question, so you can just draw directly on here. If you want to just draw the asymptotes, you don't want to draw the actual curves of it, that's fine by me. And then you can also check all of your answers on MATLAB or Python by using the Bode command. Now, first thing I like to do when I look at Bode plots, it's not really mentioned in the textbook, is when I look at this, I look at how many poles and zeros I have. And when I'm talking about just finite poles and zeros. And here we can see we only have 1 0 and 2 poles. So as the frequency goes to infinity, we're going to have a negative slope because the 2 poles each contribute to a total of minus 40 decibels per decade, while the single 0 contributes to 20 decibels per decade of magnitude as omega goes to infinity. Because once we go past all these break frequencies, we're going to see that net slope or net magnitude change. And we can see as basically as g of s, as s goes to infinity, or more accurate way of saying is s is equal to j omega, and as omega goes to infinity, the magnitude of g of omega actually goes to 0, which is shown by the Bode plot where we have the magnitude becoming more smaller and smaller. But the reason why it looks linear on this plot here is because we're using log scale. So I just like to look at that as my litmus check whenever I plot Bode plots, I make sure that when I plot all the break frequencies, my final asymptote should be either positive or negative or flat, depending on the number of poles and zeros. Okay, so here we have a system with a pole at -1, pole at minus 1,000, 10,000, and a zero at -100. And it's not really fair, but I didn't tell you how to find the starting magnitude because all you know right now is to plot the asymptotes, but you need to actually plot the asymptotes at the correct starting value. So the first step is to find the starting value. In the in this problem, we can actually substitute omega is equal to 0 because we don't have any poles or zeros at the origins. But if we do have poles or zeros at the origin, we cannot sub in omega is equal to 0. We have to we have to let omega equal to 1, for instance, and that will be our starting reference point instead. But for now, in this example, we can just let omega equal to 0 because by doing that, what we're essentially doing is we're finding the DC gain. This is like the DC gain. So what we're going to do is we're going to say G of 0 is equal to, and this is pretty easy. It's just going to be 10 squared divided by 10 to the 0 power times 10 to the 4th power. And this is why I love working with the scale here because you can just see that this is just 10 to the -2. So then when I take the log of it, 20 log of 10 to the -2, that's just -40 decibels. And that's our starting point. So -40 decibels sounds pretty small, and it is really small. It's 0.01. It's like barely a value in. So what I'm going to do now that I have my rough starting point, is like I'm going to start labeling my axes. So actually, I'm going to have this line here be my 0 decibel line. And then each of these notches is 20 decibels. So -20, -40 decibels, -60, -80. I actually think we do go down to -100. And then for our phase, it's going to be pretty flat, where we have 0 right in the middle, 0 degrees. And then we'll increase it by increments of 45 degrees. Let's get -45, -90, -135 degrees. The way I draw the frequency or I look at the frequency is I'm going to look at the smallest break frequency, which is 10 to the 0th power. And since we have 10 to the 0th power, we need to start 10 times smaller than that to account for the phase. So I'm going to put 10 to the -1 power at the starting point for the frequency. And then this is going to be 10 to the 0th 10 to the first, 10 squared. We need to cover up to 10 to the fifth power. So 10 to the fourth and then 10 to the fifth. Wow. Perfect. So now that we have this set up, and we have the starting point, I'll mark here as a starting point. And what we're going to do is we're going to draw the magnitude and phase of each pole in zero. So draw the asymptotes of each pole plus zero. So that's going to be all the phase and magnitude information. All right, so what I'm going to do real quick is I'm going to take a screenshot of this page. And I like to have this on me. And just to show you like how easy it is to save or how easy it is to read this table. All right. A little table right here. So let's start with the zero. So zero at 10 to the minus 2 or 10, sorry, 10 squared. So 0 at minus 10 squared. So then our break frequency is at omega is equal to 10 squared. So let's pick out 10 squared and right there. And the reason why we find our starting point is because we're going to have a flat line of our zero at the starting point. And once it hits 10 squared, note that it's a negative zero, meaning we have a change in magnitude of 20 decibels per decade. And we just draw a straight diagonal line like that. All right. So for the phase, we start at 10 times smaller than the break frequency. And note that because it's a negative zero, we start at 0 degrees. And then we have a change of 45 degrees per decade. So at 10 to the first power, we then have a change of 45 degrees per decade for 90 degrees. Then we flatten out. And that's the phase. That easy. All right, let's do the pole. For the pole at 10 minus 10 to the 0 power, so our break frequency is that omega is equal to 10 to the 0 power or just 1. Same thing, starting point is a flat line at minus 40 degrees. Then we hit our break frequency of 10 to the 0 power. We look, that's a negative pole with a change of magnitude of minus 20 decibels per decade. And it keeps decreasing. Come on. All right, good enough. So then for our phase, note that's a negative pole. We start at 0 degrees.
And then at 10 to the minus 1, we actually have an immediate change in phase. So up to this point, it's flat. Then we have a change of minus 45 degrees per decade for 90 degrees. And then it flattens out. And then for the pole at minus 10 to the fourth power, so that's where omega is equal to 10 to the fourth for the break frequency. Same thing, start at minus 40 decibels, hit the break frequency at 10 to the fourth power, then we decrease this, then we have a decrease of 20 decibels per decade. And then for the phase, we just start at 0 degrees. When we hit 10 cubed, we have a change in phase of minus 45 degrees per decade for 2 decades. And then now we flatten out.
So these are the asymptotes of our individual poles and zeros. And then the for the magnitude, what we're going to do is we're adding the change in the magnitudes. So when there's no change in the magnitude, it just stays the same. So I'm going to draw that in. I'll use this orange here. I'll make this a little bit thicker as well. Yeah, that's good. So we're going to be, maybe that's a little, there you go. So you see that there's no change. I'll draw this slightly above, but it's starting at minus 40, okay? So you can see there's no change in the magnitude. And then now we have a change in the magnitude by minus 20 degrees per decade. So we're going to follow this line. But then once we get to 10 squared, there's a change in magnitude by 20 decibels per decade. So minus 20 plus 20 is 0. So we flatten out at this point here. Then the second pole will cause another change in magnitude by minus 20 decibels per decade. So then we get this final line here. And that's our magnitude plot. This is magnitude of G of J omega right here. So maybe as a step, if I were to write these out as steps, I guess step 3 would be some change in magnitude. I guess the delta change in magnitude. And then sum up the angles as well. Some angle asymptotes. Same with the phase. We can see it's flat. Then there's a change of minus 45 degrees per decade. And then followed by immediate change in positive 90 degrees per decade. Followed by immediate minus 90 degrees, 45 degrees per decade from the third pole or second pole, and then flattens out like that. So then this orange line is the phase of G of J omega. All right. So that's it for today. We'll probably finish up this lecture tomorrow. I will likely release part 2 of chapter 10 tomorrow or tonight as well. Any questions? All right. Well, I'll see you tomorrow.